Hi, I'm Cassie, and I'm going to walk you through question 31 of the AAMC's official physics question pack. So this is the second question related to passage 5, which is all about electrical circuits and capacitors. And specifically, this question is asking, how do we increase the capacitance of a capacitor? So this question, very similar to the last question, question 30, in that what it's basically testing is your ability to pull up in your head an equation, in this case, the equation for capacitance, and understand the variables that are included in that equation and how changing those variables changes the total quantity, in this case, changes the total capacitance. So you should love these types of questions if they come up on your MCAT, because it's actually just a conceptual question, kind of testing your memorization of a concept and your ability to manipulate an equation, rather than a passage-specific question where you have to really understand the details of what's happening in a passage. I've noticed with my students that sometimes this trips them up because they think they have to find some sort of information in the passage and apply it to every question, and that's just not the case. Sometimes these questions are just sort of freebies if you're able to know the relevant equation. So what's going on here? Well, first, what is capacitance? Well, our general equation for capacitance is just capital C for capacitance. Capacitance equals Q, charge, divided by voltage. In other words, capacitance is just charge, our Q, stored at a certain voltage. So remember, that's what capacitors do. They store charge. So if you can just remember the conceptual aspect that capacitors store charge, you should be able to remember the equation for general capacitance, charge at a certain voltage. Now, don't get this C here for capacitance, the capital C, confused with the lowercase c, which is coulombs, which is a measure of charge. Capacitance is measured in a quantity we call farads, or capital F. So if we think about what farads are equal to, well, if we have charge over voltage, how do we measure charge? We measure charge usually in coulombs. So in other words, we have farads are equal to coulombs, and this is our lowercase c here for coulombs, divided by volt. So 1 farad is equal to a coulomb volt. And whenever you get an equation and add it to your equation deck, make sure that you always add the units like this. And you add these unit conversions too, because unit conversions are really important for the MCAT, and they're hard to wrap your head around at first. The more repetition you get, the better you'll be at manipulating these equations. So just a quick review of how you even charge a capacitor. So let's say we have our simple circuit here. We have our plates we just draw as 2 lines with a gap in between. And then of course we have our battery with our negative terminal, the small line, and our positive terminal, the big line. So what's going to happen when we connect a battery to a circuit like this that has a capacitor? Well, the negative terminal of the battery is going to repel those negatively charged electrons. So my electrons here, I'm going to draw them in orange, right? They're going to move around the circuit and they're going to build up on this one plate of the capacitor. And what's that effect going to have? Once you get some negative electrons building up on that left plate of the capacitor, what's going to happen is it's going to repel the negative electrons from the right plate of the capacitor. So our electrons then are going to get pushed back this way. If our electrons are going away from that right plate of the capacitor, then we're going to get a buildup of positive charge on that right plate of the capacitor. So here I'm just drawing a couple positive charges on the right plate of our capacitor. So this process continues until eventually you get an equal buildup of negative charge on your left plate of your capacitor and positive charge on your right plate of your capacitor. So they're always going to be equal and opposite charge. So for example, if our negative capacitor plate had a total charge of -1, then our right capacitor plate would have a total charge of +1. And at that point where that equilibrium is reached between those negative and positive charges, that's when the capacitor is said to be fully charged. And so then the capacitor can just hold on to that charge. And that's exactly what we looked at in this equation, right? That a capacitor stores charge. It's charge at a certain voltage, that voltage coming from the battery. But for this problem in particular, we're not working with just any type of capacitor. The passage tells us that we have a parallel plate capacitor. There are various types of capacitors, spherical capacitors, cylindrical capacitors, but the type of capacitor that's usually tested on the MCAT is just parallel plate capacitors. And as it sounds, just like we drew here, right, a parallel plate capacitor are just 2 plates that are parallel to each other. So we have a more specific equation for capacitance that is just for parallel plate capacitors. So the equation for parallel plate capacitance, I can remember with the word caked. So on the left side of our equation, we have a big C for capacitance. And then on the right side, we have A, K, E, little e, divided by D. So what do all these variables mean? Well, our A is our area of overlap between our capacitor plates. What does that mean? Well, in general, for capacitors, they're going to be perfectly lined up, those 2 plates. So in that case, the area of overlap would be the entire region of the plates. But occasionally, you'll see a capacitor where the plates are not perfectly lined up. So where would be the area of overlap between these 2 plates? It would just be here, right? This area here and this area here is not overlapping between the plates. So that's what the area of overlap means. Now, our K is just our dielectric constant. So what the heck is a dielectric constant? Well, sometimes we might want to increase the amount of charge that a capacitor can store. And one way to do that is to put what's called a dielectric material between our capacitor plates. So let's just say I put a material that's considered a dielectric material here in green between my capacitor plates. A dielectric material is an insulator. An example of a common dielectric material is PET, P-E-T, in capitals like the plastic bottles. Insulators prevent charge from flowing. And so when you put that insulating material between your capacitor plates, you're reducing the strength of the electric field that is between them. And by doing that, you're therefore going to allow more charge to keep building up onto the capacitor plates so that you can achieve a higher level of capacitance. So anytime you have a dielectric material that's put between your capacitor plates, it increases your capacitance. And we see that right in our equation here because our K is in the numerator of our equation with our capacitance on the other side. So we know there must be a direct relationship whereby if you increase K, you increase your total capacitance. Now, in this case, if you read the passage, they don't talk about any dielectric material. So when you have a problem that talks about the capacitance of a parallel plate capacitor, but there's no dielectric material, you can just leave this K entirely out of the equation. And then you would just have C equals A times E divided by D. Then we have our lowercase e. What does that mean? The permittivity of free space is just a number that tells you how much a vacuum allows an electric field to do its thing. So for the purposes of the MCAT, you don't really have to understand what this value represents. What you need to understand is that it's in this equation and it's in, again, the numerator of this equation. So since it's in the numerator of this equation, if we increase our E value here, our permittivity of free space value, we're going to increase our total capacitance of our parallel plate capacitor. So that E value would be given to you in a passage if it's relevant and you need to use it. Now, finally, in our denominator here, we have D. And D is going to represent, as usual, distance. In this case, it's going to be the distance between our plates of our capacitor. So in other words, I'll draw in blue here. Our D would be this distance here between our plates. Okay, so now that we understand the equation and what variables go into our equation for the capacitance of a parallel plate capacitor, let's take a look at our answer choices. Well, A talks about replacing a higher resistor with a lower resistor. Do we see an R anywhere in this equation here? No. So resistance is irrelevant to the capacitance here. So that means we can eliminate which of our answer choices, any of them that have to do with resistance. In this case, that looks like just answer choice A. Answer choice B talks about the voltage of the battery. Again, do we see anything in our equation here that talks about the voltage of the battery? No. So we can also eliminate B. Answer choice C talks about increasing the separation between the capacitor plates. So now we finally have a variable that's actually in our equation. So we have to think through whether the increasing makes sense here. Well, our distance between our plates, our D, is in the denominator of our equation here. So if we were to increase D, we know the inverse is going to happen to the thing on the other side of our equal side, to our capacitance, since anything in the denominator is going to have an inverse relationship with the thing on the other side of the equation. So if we increase D, we're going to decrease our capacitance. And notice this answer choice, which wants us to increase our capacitance. So we're going to eliminate this answer choice too. So that leaves us with answer choice D, increasing the area of the capacitor plates. Let's double check to see why that's correct. Well, area is in the numerator of our equation here. So it's going to have a direct relationship with the thing on the other side of our equal sign. So if we increase our area of overlap between our capacitor plates, we're going to increase our capacitance. So that's why the answer is D. Now, even though this next equation I'm going to show you isn't directly tested in this question, since we're reviewing the important capacitor equations you need to know for the MCAT, I want to make sure to quickly review the equation for the magnitude of a uniform electric field between capacitor plates, because this should be in your equation deck for the MCAT. So we're going to have our capital E, the magnitude of our electric field between our capacitor plates, is going to be equal to our voltage that's applied to those capacitor plates. So that's going to be coming from our battery divided by the distance between our capacitor plate. And again, this only applies for a uniform electric field between capacitor plates. What are going to be our units here? Well, we know that voltage is always measured in volts, and we know that distance is always measured in meters. So one way of expressing the units for our electric field would be in volts per meters. So I hope this helps. If this helps, please give the video a like and follow my channel for more content like this.